Okay, chemistry 2 time. We're going to talk today about equilibrium. Let's write it down. Instead of talking about whatever you guys are talking about, let's talk about equilibrium. Equilibrium. Define it. You should be able to do this. You had it in your vocab. What are some things that are in equilibrium? Didn't Mr. Leverchuk give you like a hard quiz about this? And then when he emailed me back, he said, even though they didn't know anything about it, they tried their best. And I was like, well, that's kind of the point. You're not supposed to. We did the lab. and you also did. Anyway, equilibrium. Define it. I'll give you a sentence frame. How about that? A state in which what?
Things are equal.
Okay, yeah. Okay, so we could say in which processes are what else could we say? Equal is a good way to. We could almost think about it like they're canceling each other out, but that's not. I don't want to put that. I certainly don't want to put that because that's not a good science. But a state in which processes are equalizing one another. This is kind of a cop-out because it kind of uses like part of the word equilibrium. But there are lots of types of equilibrium. There's one right there. Do you see it going by on the highway? Car. Yep, car. Good. Yeah, Asher does that too. What is that, Asher? Car! What's the car say? Yeah, anyway, yeah. Anyway, so here's a 2015 Chrysler 200 with a really long trunk, apparently.
Oh my god!
Chrysler.
It says equal in the R.
Does it use equal in the vocab?
It says equal. Looks like it's to its coefficient in a.
So when I say processes here for the Chrysler driving by, we're going to say it's at a constant velocity. Constant velocity. This is more about physics than chemistry, but this is just an example. Equilibrium is one of the CCCs, one of the cross-cutting concepts that applies to all sciences. Look there. See the green one at the end there, stability and change? That is about equilibrium. The example in that picture is evolutionary equilibrium, sometimes called punctuated equilibrium. But in our example here, yeah, so it's going to change a little, but it's going to equalize. We can almost think of it kind of like in biology, a negative feedback loop, where things eventually equalize out. But we have a constant velocity here, so it's moving at a constant velocity. Oh, there's another one. Truck. What's the truck say? All the trucks are diesel trucks to Asher.
Like the good pop stuff when
yeah. Ni hao. That truck is at equilibrium. Ni hao. Look. So what processes are acting on this Chrysler 200 2015?
maroon.
Oh, maroon. Burgundy.
No. In the burgundy.
Oh, you're right. No, but we really have to get this going. So tell me, what kind of processes, when I say what processes are acting on that, what do I mean in physics or physical science? You remember this?
Like friction.
Yes, okay, like friction. Which way is friction acting?
On the tires.
On the tires. So it has some friction acting on it. Friction, what else? It has,
Wind?
okay, maybe a little wind. What else? What must be true if we have both of these forces acting right?
Gravity.
What must be acting, must there be something acting left? Well, yes, if it's in equilibrium, it must be. What is acting left?
Acceleration.
Yeah, it's burning some fuel, some thrust. It has some thrust. Gravity is acting on it. This is not to scale. The force of gravity would certainly be stronger than the thrust of this vehicle. Is anything pushing up on it? Do you remember what this is called? This is, no, not convection. The normal force is acting up. The road is holding it up. That's the normal force. These are in equilibrium. They are true. They are processes acting on this, but they're equaled out. They're canceled out. No, let's not say that again. But they're equaled out by another force. The same thing happens in chemical equilibrium. We can have substance A plus B is in chemical equilibrium with, this is the little symbol we use for chemical equilibrium, with substance AB. What's this little arrow mean? This is not a normal arrow. It means It means it's in equilibrium with, and what does that mean relating to what we just said? Can A plus B yield A? Then both any given set of circumstances. Well, if I had some water, which I don't because the Culligan won't deliver anything at Culligan, comment disabled for this video, but if I have some water in here, which I don't, but if I have some water in here, boop, if I have some water in here, I'm just showing the YouTube people, the one guy who has to watch every YouTube video, I refuse to believe he doesn't exist, has to review every YouTube video. When there's water in here, the water at the surface is always in dynamic equilibrium. Like it's in equilibrium that's constantly shifting depending on the conditions. So here's my vessel. This is what it looks like to me. It looks like the little bird from those hilarious YouTube videos about birds. Anyway, you know what I'm talking about. So this is liquid water, H2O sub L. And this up here, there's some H2O sub G. And every single second, some of this becomes this, and some of this becomes this. And it happens the other direction too. Over time, is this equilibrium stable? If I leave this out, will this equilibrium continue? No, what's going to happen if I to my vessel with water? What will it look like? It'll be water. So over time, eventually, a little bit more of the liquid becomes gas than the gas becomes liquid. But this isn't happening right now. Oh yeah, great example. My Valentine's Day fountain. I'll just show you another empty vessel. Here in Crawford, we're thirsting to death because the Culligan didn't get delivered. Another empty fountain. But over time, there must be more liquid water becoming gaseous water. So is this a stable equilibrium? No, there is equilibrium because still some gas is still becoming liquid. So it's still in equilibrium, but over time the equilibrium is unstable. Do you understand a little bit the concept of equilibrium in general? Your bank account is in equilibrium, probably, I would assume. I don't know your life. But you have some outflow of money, you have some inflow of money. Yep. You don't have any inflow of money? None, Dally? You don't make any money? How do you afford to go get pizza every single day? Good. Good for you. Law of chemical equilibrium. Let's look at that. The law of chemical equilibrium states that at a given temperature, a chemical system might reach a state in which a particular ratio of reactant and product concentrations is a constant value. That's chemical equilibrium. The ratio of products and reactants is a constant value. The general equation for reaction and equilibrium is as follows. Let's write the equation they give us in the book instead of my kind of simplistic one. A plus B is in equilibrium with C plus D, where the lowercase letters are what? Are coefficients. I don't know how many I's are supposed to be in that. And the uppercase are what? Yeah, they're substances. I'll put substances. I was going to put species, but math. KEQ, lowercase k sub EQ, equals our best friend. What's this mean? Do you remember? In the last chapter, what's this mean? Yeah, the concentration of substance C to the Cth power. That's nice, I like that. Times the concentration of D to the Dth power. Thanks, Peyton. Over the quantity, the concentration of A to the 8th power times B to the Bth power. You know how about people are always in chemistry talking about things to the Bth power? Just give me a break, Peyton, for heckling me. But now, do you see? I hope this makes it clear to you. One of the reasons your book puts chapter 16 before chapter 7 is like a stupid thing, but the reason why chapter 16 is because if you talk about this first, people get used to seeing that the coefficient forms the exponent of this equation. Do you remember my specifically telling you in the last chapter that the coefficients have nothing to do with the rate law. Remember that? But in this they do. You don't need experimental reaction rates for this. All you need to have is the balanced chemical equation. So, try this another way that'll make it a little bit easier to understand. The equilibrium constant for any reaction is what? Tell me what words. Well, what is yeah. Yeah, there you go. Concentration of the products, and obviously those things need to be raised to the power of their ratio over the concentration of the reactions. So basically, this is a ratio of amount of product to amount of reactants. And when that reaches a set value, the KEQ, set value, this is the equilibrium constant. And that's what we're trying to find here. Could you solve this any direction? Like if I tell you the KEQ for this reaction is blah, blah, blah.
What the heck does it say?
Products. Products. I'm doing my best, Skylar.
It's like
Okay, it doesn't matter what it looks like, because what it actually is products. Your book defines homogeneous and heterogeneous equilibrium. I expect you to know about that. We're going to talk about Le Chatelier's principle a little bit, and then there's some more stuff in here that you need to know, but I'm just going to trust that you know it because you've already done it. But I don't think I'm trying to look to see if there's more math. All the math in this chapter stems from this equation, so if you can do this, should be good. Like for instance, there's a solubility product. And we'll talk about those specifically, but this is the general math. And then the specific ones we'll talk about tomorrow when we go over the chapter review. But I do want to touch on Le Chatelier's principle first, okay? Just to make this video brief. Le Chatelier's principle, I'm going to erase the beautiful Burgundy Chrysler 200 2015. What, does it have a 3-liter engine, Dally? Whoa! You can really tear up the road with that thing, huh? Is it a V6 that he has right now? Oh, okay. It doesn't matter to me. Le Chatelier's principle. Oops, we have to capitalize the man's last name.
Hey, tell us.
Oops, I put the chapeau over the wrong letter. There we go. Le Chatelier. This, just so you know, this in French, this little thing means that in Old French, there was another consonant after this that has been omitted in modern French, but it also makes it look cool. Like you know about a chateau. A chateau is a castle, but they omitted the S from Middle French, and so it's just chateau with a.
Sounds like we're from Paris.
There you go. That's a chateau, and anyway, it doesn't matter. The man's name is Le Chatelier. It's the name Henri Louis Le Chatelier. Can I write it in English? No, because this is a person's name.
What is that?
This little thing is an A with a hat. Avec un chapeau.
It's E-L-I.
It's also in your book. If you had your book open and your cell phone was not on top of it. Le Chatelier's principle says if your phone wasn't on top of it. Why don't I? Le Chatelier's principle in English.
We're in Spanish here, okay? I mean,
It's not dissimilar. Le Chatelier's principle says that any stress, this is going to be in English, any stress, stress, I don't even remember. Stresso, I bet that's it. Any stress on a system shifts the equilibrium in the direction that relieves the stress. What does stress mean in this context? What do I mean by, I mean like I'm going to call substance A's mom and tell him that he's been bad at school? That would be stressful? No. I don't necessarily mean even physical pressure, although that can do it. What does any stress mean? No, these can't be uncomfortable because they're chemical substances. What do I mean? I'm sorry, Scott. I'm not trying to shoot you down. But what do you think I mean by stress? It's going to have to be something real and physical. It can't be its feelings. Yeah, what other things cause this?
Color.
Probably not. Certainly. Temperature. Pressure, temperature, those definitely could. Amount would change it, concentration. But all those things are just changes. So what I mean, when I say stress, I just mean any physical change that happens to the system shifts the equilibrium in the direction that relieves that stress. And those are, there are actually four. We forgot one. These are the stresses. Changing concentration of reactants or products. For example, if in this equilibrium, in this equilibrium reaction, if I add more C, how is the stress going to shift this equation? Oh, and first of all, we say left or right. That's what we say. When I say left, I mean more of this will be formed, more of the reactants will be formed. That's called a shift left. Would be a shift left, because the reactants are on the left, means that more reactants are formed. And a shift right means more products are formed, okay? So if I add more product, how's it going to shift it if I add more products? Yeah, it'll shift left. Adding products means a shift left, okay? What if I take C out? If I'm removing products, it'll shift right. What if I add B? Yeah, it'll shift to relieve the pressure. It'll do the opposite of what you've done, basically. That's a really, really almost borderline condescending way to phrase it. But if I put B in, what's going to happen? I'm shoving B into this reaction. It'll shift right. What if I'm taking B out? Yeah, it'll shift left. Okay, so that's the changes in concentration. And in fact, there's a lot of industrial chemical processes, like when they make chemicals, for me to use in the lab, for instance, when they make chemicals, they will move the product because it'll make this reaction happen faster. Okay, so a change in concentration. We already said change in temperature, and this one, I might get this wrong, so if it is wrong, please leave a comment. Comments are disabled for this video. But if this is an exothermic reaction, which has a higher energy? The reactants or the products? If it's exothermic, do the reactant products have higher energy? The reactants have exothermic. So if I increase the temperature, is that going to shift it right or left? So think of it this way, like exothermic, the heat is kind of like a product. If this were exothermic, the heat's kind of a product. So if I'm adding more heat, it'll shift left. Yep. So that's kind of, and I would encourage you when it comes on that time, if this, whatever, just endothermic heat is a reactant and exothermic heat is a product. Just think of it that way. Change in pressure. This one, once again, it'll depend on which is how the pressure changes as the reaction proceeds. Your book will have things to say about that. And then is catalyst or inhibitors. Remember, catalysts and inhibitors are neither products nor reactants. But what do they do? What does a catalyst do? Speeds it up. Inhibitor slows it down. And so that'll shift it either right or left too, depending on which one of those you use. Yep. Oh, my hot water is done. Boop. Okay, and then your book also talks about the common ion effect, which it relates to Le Chatelier's principle. But basically, if there's more than one reaction or product that has, it can shift it left. And that's a vocab word, so you just need to study up on that. Questions about how this math would be done? I mean, we've done it. In a normal lesson, like we will now be doing the math, but you've already done this, so you understand how this works fairly well. Effectively, it's plug and chug. I mean, you just shove in whatever A is on the bottom, raised to the power of however many there are. But do you have specific math questions that you think?
That's the coefficients difference?
In one, yep, the coefficients are the powers here. And specifically told you not to, but that's because usually people are familiar with this one thing to do. And so it becomes, you have to be careful that in a rate law you're not. cause a completely different set of circumstances. Question. So what I'm looking for, you need to understand this conceptually, like what is going on when a substance or when a reaction is in chemical equilibrium. And really, if we get right down to it, all chemical reactions are to some degree equilibrium reactions. They don't always appear that way, but under a certain set of circumstances, any reaction is possible. And then you need to know, obviously, all your vocab. This is the main math you're going to be doing, and then Chatelier's principle is, there'll be something. How will the reaction shift in this set of circumstances? It can be kind of confusing to keep straight, but this is pretty much all conceptual. Like, none of this is very math heavy. This is. Well, I wouldn't say math heavy, but this is. And what kind of things do we plug in here? Some kind of, usually a molarity. It might be a molality, but usually a molarity. Other questions?